Thank you very much, Lisa. Yes. So today we're going to talk about multi-way analysis, and specifically we're going to talk about Parafac. I know that some of you have worked with Parafac, but I'm going to start with the beginning, so to explain all the details and also show a little bit about how we work with it in practice in MATLAB. Now, I'm actually also going to mention some other methods. For example, Parafac is an extension of PCA when you have more complicated data, but there are other extensions as well of PLS, etc., and some of them are very interesting. So, for example, if you work with GCMS, then this, which is called the Parafac 2 model, is extremely interesting, and I'll show you some examples of that. But first we need to discuss what freeway data really is. Now, normally when we work with data analysis, we have matrices. So we have an Excel sheet. So maybe you have measured different samples, and on every sample you took a spectrum. That's a matrix, and you can have it in one Excel sheet. But very often your data is a little bit more complicated than that. Maybe you measured a spectrum of this sample at 5 different time points. So you really have 5 spectra of this sample and 5 spectra of the next, etc. And that would actually give you a freeway array, a box of data. And there are many situations where you get freeway data. Here's just a few examples from my kind of applications. So for example, sensory analysis, where you have different food samples, for example, and then you have 20 different judges, and they all assess these food samples with respect to 30 different qualities. What's the saltiness, what's the earthy flavor, what's the off flavor, what's the sweetness, all these things. That's a freeway array. Or in process analysis, if you have different batches of data, you monitor the variables over time. Now you can see there's a lot of places where you have freeway data instead of just normal two-way data. And it's a little bit complicated because when we do data analysis, we normally use linear algebra. Now linear algebra is only related to matrices. When we have a freeway array, we don't have a similar notation. And that actually makes papers, if you want to read a paper or a book about multi-way analysis, it's very complicated because there's not a beautiful notation. But actually, freeway analysis is not very complicated. It's not very different from normal PCA or PLS. It just looks more complicated because the notation is really stupid. We don't have a really nice notation. But don't be discouraged by that, because it really isn't that difficult. So what can we do when we have freeway data? Well, for example, if we want, we could unfold the data. That means we turn it into a matrix. So I could take all the spectra here and put them here. And then the spectrum at the next pH value and put them here. And now I have a matrix, so I can do PCA or I can do PLS or whatever I want to do. And that's fine, but it's actually not a really good idea, and I'll explain why. Well, first of all, it's complicated because now there are 3 different ways that I can unfold the data. And also, this is going to be very long. Imagine that I have, let's say I measured, 100 variables and 10 pH values. So that's sort of 110 different things. But when you unfold the data, like here, that's going to be 100 times 10. So that's going to be 1,000 variables. And that means that the model I built here is much more complicated mathematically. And that specifically means it's going to overfit. Well, there's a high risk of overfitting when you unfold your data. That means you get less accurate models. And the good thing is, whatever you want to do, if you want to do PCA, you can also do freeway PCA. it's not called PCA anymore, it's called either Parafac or Tucker. So that's two different ways of extending the PCA model. We are going to focus on Parafac, but you need to have an idea about what the Tucker model is. Or let's say you want to do PLS, then you can do multi-way PLS. So you don't have to do the unfolding. Instead, you can actually just work directly on the data. And there's a lot of advantages in doing so. Okay, let me just explain some notation, which is not really important, but it's nice to know, especially if you want to look into the literature. So we normally call this a three-way array, but it's also sometimes called a third-order tensor or a three-mode array. And the word tensor is really good if you want to scare people, because most people are afraid of tensors because it sounds very complicated. But it really isn't. But if you're working with mathematicians and say you're doing tensor analysis, they will shut up. Typically when you do chemometrics and say, oh, I'm doing PCA and PLS, they're not very impressed. But if you say you're working with tensors, they will be really, really impressed with you. But it doesn't matter, it's all the same here. So three-way array, third-order array, or three-mode array. One thing we don't do actually is that we usually don't call it a three-dimensional. Wow, that's an ugly handwriting. We don't call it a three-dimensional array because we actually use dimension to talk about how big is the matrix. If you have 200 wavelengths, that's a 200-dimensional space. So it's better to avoid this word. Not a big deal. People will understand. But it can be confusing because we use this word for several things, and it's good to avoid ambiguities. If I take out one of these matrices to the front here, I usually call it a slab or a slice, just to make it difficult. But that's the word people are using. But it's just a matrix. One of these will be a sub-matrix, and that's also called a slab or a slice. Okay, anyway, let's have a look at the most basic model. So that would be PCA. And let's save this one a little bit. Here's a graphical representation of PCA. I have a matrix, that's my data. And now I model it with some components. This is component one. And we use the terms here in multi-way analysis, A and B. So A would be score one, and B would be loading one from PCA. And here's a second component, and I can add more components if I want, but this is a two-component PCA model with score one, score two, loading one, loading two. And I can put them together, so I can have score one, score two, loading one, loading two. This is just linear algebra. Now, as I told you, there's no nice notation for three-way arrays, and that makes it a little bit complicated. Because normally, if I would write the Parafac, the PCA model, I would write it with matrices like this. This is the notation that most people that work with PCA are familiar with. But I cannot extend that to three-way arrays. So instead, I've written it here in the scalar notation, and it's not very intuitive. But I'll explain what it is. What it says is that this is sample I, variable j. So on sample number I, on variable j, I measured something. This is the absorbance I measured. And that is modeled by the scores of sample I times the loadings of variable j for all components. It doesn't matter that what you have to accept here is that this is probably PCA. This is probably the same as this. That's the important message here. But the nice thing about this notation is that I can show you how to do a three-way model. Because imagine we now had a box of data like this. Well, if you see here the difference, I just add another set of loadings. So if this is PCA, score one, loading one, then this is Parafac. Score one, loadings for the variables, for example, and loadings for the other variables or times or whatever. And here you can see that with this stupid scalar notation, it's actually very easy to extend because you just add one more parameter. But the main thing is to see in the graphics, see that it's kind of simple. This is the only difference between PCA and Parafac. We just add another set of loadings. And you can also see here that it's very easy to do four-way analysis. If I have a four-way array, I just add another set of loadings, or five-way, or nine-way, or 200-way. It's not difficult. The difficult part is going from PCA to three-way Parafac. So this is called the Parafac model, and it was developed by Richard Harshman in 1970. And he was a really brilliant guy. He developed it based on some very basic ideas from the 40s in psychometrics. But he was the one who made Parafac popular and useful. He comes from psychometrics, so just like chemometrics, they have psychometrics. But it was really chemistry that made Parafac popular, because there's some really nice applications of Parafac in chemistry, especially with fluorescence analysis. Just want to mention something. If you have a matrix, and let's say I can describe it perfectly with 5 PCA components, then that matrix has rank 5. That's the definition of rank. Not the normal one, but it is the definition of rank. If I can describe a matrix with 5 PCA components perfectly, not with residuals, but perfectly, then it's rank 5. If I can describe it with 19 components, it's rank 19. And it's the same for freeway arrays. If I can describe an array with 8 Parafac components, then that matrix, that freeway array would be rank 8, for example. So it's kind of similar. But there are some very important differences in how a Parafac and a PCA model works. I don't know if you're familiar with the properties of the PCA model. This is a really beautiful picture of a PCA model. It's called component number 1, 2, and 3. Now the PCA model has what we call rotational freedom, and that means that it's not well defined. Imagine, let's say I make a, too many things here. Imagine that I make a score plot, like score 1 versus score 2, and I make a loading plot. I can actually rotate my scores and loadings, and it makes no difference. It's kind of arbitrary, because the interpretation would be the same. It's just the coordinate system. Now to fix that in PCA, we introduce something. The first component has to describe the maximum variance. So there's no other component that will describe the data better than this one. And the second component, well, the score has to be orthogonal to this score. The loading has to be orthogonal to this loading. These are kind of strange mathematical constraints that we put on our model to make it unique, so that every time I do PCA on this one, I'm going to get the same thing. Let me show you how it looks. Let me take a data set. We got sound. Let me turn off the sound. So let me take a data set, and it's actually going to be one that we're going to use the rest of the day, or the morning. I'm going to work in MATLAB. And never mind what I'm doing right now. Okay. So now what I have is a fluorescence landscape. It has 201 emissions and 261 excitations, and I'll show it to you. Maybe I'll turn off the font a little bit. Whoa, okay.
I can see that.
You see? Yeah. That's nice. Okay, the screen is going to be a little crowded, I guess. Never mind what I'm doing now. I do a lot of MATLAB stuff. But this is a fluorescence landscape. This is one sample measured at, I didn't put the axis on, but measured at 201 emissions and 61 excitations. Does it make sense that this is a matrix? So in each element, so the first excitation and the first emission, I have an intensity. That's the number. So all the elements are just the intensity, actually the photons counted. So this is one matrix, one landscape.
One sample.
One sample, just one sample. And you can kind of see that it has free components. So it's probably rank free. Let me do PCA on this one. And I'm gonna use, so today what I'm using is a software package called PLS Toolbox. That's not important, but that's the one I'm using for doing my analysis. And tomorrow I'm gonna talk about all the things you can do in PLS Toolbox. But today I'm just gonna use it to build some models. So let me make a free component model on this data set. And let's take a look at the scores and the loadings of this model. So these are the three first, here we are. These are the three loadings that I get when I do PCA these are the loadings in the excitation mode. And you can kind of see that the first one looks like, let me show you, I still have my landscape course. Here we are. So this was my actual measurements. These are all the emission spectra that I measure, and I get loadings like this. If you are used to doing PCA, this makes sense. The first component looks like the overall shape of my excitation spectra. And the second and the third ones are more difficult because they are forced to be orthogonal to this one. So I'm not getting the real chemistry, but I'm getting something that reflects the underlying information. And that's what we assume, that's what we normally get out of PCA, so that's perfectly fine. But we would like to get a little bit more information out of this. We would actually like to really be able to see what are the real underlying constituents here. With PCA we cannot do it because these components are forced to be orthogonal to each other. PCA forces these to be orthogonal. And I know that these real underlying spectra, the pure spectra here, they're not orthogonal at all. So there's no way PCA can find the real chemistry. And that's a little bit annoying. Well, let's go back to Parafac. Yeah. So let me show you an example of a data set. We work a lot with environmental monitoring where we take water samples from whatever and measure the fluorescence because that reflects the organic matter in the sample. That's what you measure. So it's good for monitoring pollution sites or checking the sort of dynamics in the ocean, the carbon cycle basically. So you get a lot of information from simply measuring the fluorescence of water samples. And I guess most of you are familiar with fluorescence, but let me just shortly explain it here. So what we do is that we take a sample, like this one, and we send in light at one particular excitation wavelength. So maybe 300 nanometers. And then we measure the emission at many wavelengths. So for every excitation, we get a complete emission spectrum. And we do that for many excitation wavelengths. And that's why we get this excitation emission matrix, or EEM as it is called. And the nice thing here is that essentially every peak represents one fluorophore. Not all chemicals fluoresce, but some do. And at least in many circumstances, one peak will represent one particular chemical. These things here are not chemical. That's an artifact in the data, and we'll get back to that later on. This is Rayleigh scattering, and it doesn't represent the chemical information. That's something else. Well, anyway, in environmental monitoring, what people do is measuring fluorescence landscapes. Here's one fluorescence landscape, plotted either as a landscape or as a contour plot. This is the traditional approach for sort of plotting these things. And it really, until a few years ago, the state of the art was to look at them. And then you would say, we have something down here, so that's proteins, or up here we know that we have some NADH and things like that. So people would look in different areas and just visually interpret it. And that's not very extensive use of this. There's a lot of information here, and there's a lot of things you're going to overlook if you only look at this visually. Now, I showed yesterday, but I'm going to show it again, how we can actually interpret these data. So here we have one particular sample. Let me see if it wants to run. Oh, God damn it. I'm sorry. The movie is not working. Let me find it. Here we are. So, let me go here. Open fast. Wow, what's that? That's crazy. Here we are. So here's the landscape where you see a peak and a shoulder. And actually there's a third shoulder, but it's so small that you don't see it. So visually you wouldn't see what it was. But as I also explained yesterday, if this measurement follows Beer's law, and it will sometimes if the conditions are right, then the contribution of every chemical